All right, so welcome back. We are now in week 10, almost 2/3 of the way through the semester. And this is now lecture number 19, I guess. And we are continuing on chapter 15, which is on correlation, scatter plots and correlation. And so let's go. So when you have a scatter plot or correlation question, you're going to have the x-axis, you're going to have the y-axis, right? Our scatter plots go on a coordinate system where you have the x horizontal axis and the vertical axis. And the question is, which one goes on which? Which variable should be along the x-axis and which variable should be along the y-axis? So essentially, there's two different types of problems. One is just a situation where you have two variables that are connected, but you don't really feel that one really influences the other. Versus a completely different scenario where one does influence the other. So for example, if I'm trying to find a correlation between how many hours of sleep you get and how many yawns how many times you yawn the next day. So hours of sleep versus yawns. I think it's fairly obvious that the sleep that you get determines or helps explain how many yawns that you make versus how many yawns explaining how many hours of sleep. There's clearly a proper direction for one variable helping to explain the other. So when you have a situation where one variable explains the other, you want the first one, you want the explanatory variable, you want the one that explains to be along the horizontal axis, and you want the response, the one that depends upon the other, to be the y-axis. And if neither really explains the other and you're just looking at a correlation between them, is there a connection? Then in that case, it makes no difference which is on the x and which is on the y, because we know the correlation coefficient will be the same in both examples. So looking at the following examples, was the right choice of x and y made, or did it not matter which was which? So you have years of schooling versus the fertility rate. This was the first thing that we saw earlier, right? Would you say that years of schooling might explain the fertility rates, or fertility rate explain the years of schooling, or neither? Which one would help explain the other? I'm not on mute, right? You all can hear me?
Yeah.
So for years of schooling and fertility rate, which one explains or helps explain the other?
I would say probably the years of schooling affect the fertility.
I would think so, right? I would think so. Again, it's not a causation, it's a correlation. Then we had the Hershey Park example. I'm pretty sure that was the length of ride versus time, right? We had that one example, length of how long the ride is versus how much time the ride takes. So which one of those do you think is more likely to explain the other, if either way? Would the length help explain the time, or the time help explain the length? Or both, or neither? This one I kind of, go ahead.
Time.
Say go.
Length explains time.
Well, length will certainly explain time in the sense that the longer it is, the longer you expect the ride to take. But at the same time, the longer it takes, the longer the ride should be. But if I had to give a direction, certainly the way you said it is correct, because the length of the ride should explain the time as more of a causation, even though we don't do causation. But it certainly explains the time versus time explaining length. I think the right direction was chosen there. arm span. We had an arm span example, didn't we? What was that? The arm span example. Wasn't that yeah, was it here? Arm span and height. Would you say that arm span is more likely to predict height, or is height more likely to predict arm span? And I guess that's probably a better way of thinking about it in terms of predictions. We want the X to predict the Y. So would you say that height is more likely to predict arm span, or is arm span more likely to predict height?
Height explains arm span.
I certainly agree with that. CSUN High Schools. What was the CSUN High School example? Here, average SAT verbal scores of entering CSUN students and the percentage who get a grant or a scholarship. So when we did the scatter plot, it was the percent with grants or scholarships on the x-axis and the average SAT verbal scores on the y-axis. Was that correct, or is it more likely that the other one that it should go in the other direction? Should it have been average SAT scores on the x-axis with percent on the y-axis? Did they do it correct the way they did it? Could it have gone either way? Is neither one better? Does it not matter?
I think they could have done it where the SAT scores are more likely to predict the percentage.
Yeah, I agree with that, because if you think about it chronologically, you take the SAT before you get to college, which means the average SAT scores chronologically come first. So I think average SAT scores is more likely to predict grants and scholarships versus the other way around. But again, correlation, you get the same answer either way. So single parent versus high school graduation rate. Single parent versus high school graduation rate. So the number of single parents, because it's got to be a quantitative variable to be a scatter plot. So graduation rate would be on probably the y-axis, with number of single parents being on the x-axis. Right? Being a single parent, I think you're more likely to ask, how likely is it to graduate? How long will it take to graduate? Versus how long it takes to graduate, saying, oh, are you likely to be a parent? Right? I think a single parent certainly should be the x-axis. And then ice cream and temperature, again, I would think temperature should predict ice cream, not the other way around. So that all kind of makes sense, right? Seems reasonable. Anyone?
Yeah.
Okay. All right. Anyways, so this is the big no-no amongst statistics, or the big warning, the caveat. Association does not prove causation. In other words, just because there is a connection does not mean one causes the other. For example, people who read better usually have bigger feet than people who do not read better. This is a fact. The length of a child's foot has a positive correlation with the child's reading level. But the longer the foot on average, the better the child can read. Statistical fact. Does this mean that reading better causes the children's feet to be bigger? Would that be a logical conclusion to the fact,
It wouldn't be.
That doesn't make sense. Does having bigger feet cause a child to read better in the first place?
No.
I would hope not. It doesn't really seem to make sense. But yet it's a statistical fact that people with bigger feet, children with bigger feet, tend to read better. So what might be the lurking variable that's behind the scenes going on that's connecting them?
The older they get, the better they get at reading.
Say again?
The older they get, the better they get at reading.
Exactly. Children with bigger feet are probably older than children with smaller feet, and children who are older have had more years of schooling and therefore are probably better at reading. So the lurking variable behind the scenes is just age. So yes, statistical fact, bigger feet, better reading. But behind the scenes, lurking behind the scenes is this lurking variable, age. Seems reasonable, makes sense? I hope so. It's a big mistake people make is thinking just because there's a correlation that one causes the other. There could be things going on behind the scenes. So association does not imply that an increase in one causes an increase or possibly decrease in the other. Often, an association between two variables can be due to a lurking variable or even to just a coincidence. What is a lurking variable? It's a variable that you do not include in your analysis, but that explains the relationship between the variables that you did include. It's lurking behind the scenes. So this plot here shows results of a test on fractions and the weight of randomly selected students from a middle school. There seems, according to the graph, to be a very clear correlation that the more a person weighs, the better their score. Do you agree with that based upon the graph? The further to the right you are, the more you weigh, the further up you are, the higher your test scores.
Yeah, it does show that.
The statistics is clear. Would you say then that if you want to do better, you should put on some pounds? And this could explain why I do so good at math. Who knows? Does that make sense? You want to do better? Just put on some weight, huh?
Sure.
Well, off topic, but do I have a bird in your classroom? I am not in my classroom. I'm actually at home. This is not my classroom. This is my office.
I figured because of the board in the background.
Yeah, no, that's a board that I put up because last year during the pandemic, I was teaching from home for the most part, and I didn't have my iPad or anything, so I bought a board that I put it up. But yeah, this is me. This is my casa. This is my house and whatnot, or part of it anyway. But yes, we do have a bird. We do have a bird. That's I rent out a room, a friend of mine, and she has a bird. Yes, so let's bring the bird over. They all want to see it. Come on, come on, come on. There's the bird.
Oh, so cute.
Hello, hello, hello,
The yellow head.
hello. You're on camera. Smile. Smile. What type of bird? What type of bird is this? Just a parrot?
A parrot called a sun conure.
A sun conure. A sun conure parrot. So, hello. Okay, anyways. Yes. Thanks. Till next time. So anyways, we do have a bird. And you just met the bird. The bird's name is Amigo, which, if you don't know, is Hebrew for annoying creature. No, I'm kidding. I'm like,
it's Spanish, but oh, okay.
It was a joke. Yeah. Oh, she did not like that. Okay. Anyways. So yes. Okay. So where was I? Right. So the question was, thank you for that lovely tangent. This will be on video on YouTube for the world to see forever. Okay. So back to the original question. If you put on weights or if you weigh more, if you want to do better, does that mean that you should, sorry, I wasn't, try it again. Yeah, if you want to do better, should you just put on weight? Because there's an obvious correlation. The more you weigh, as a general rule, the better you do. So does that seem like it makes sense? And again, the answer is no. It's not that the weight causes you to do better, but as a general rule, who weighs more? People that are older. And people that are older are probably going to be better at math than people who are younger. Right? Makes sense? So again, there is a lurking variable age that's going on behind the scenes. Right? We agree?
Yeah.
Okay. So we talked about that. Okay, so we're not going to do everything because we're kind of going slow this semester, which is not a horrible thing. But we're missing 2 days. We're missing next Thursday. By the way, guys, we don't have class next Thursday. It's Veterans Day. And 2 weeks after that is Thanksgiving. We don't have that Thursday either. So we're missing a few days. Okay, this one's fun. Each of the following associations is caused by a lurking variable. Identify possible lurking variables for each. So 1A, there's a strong positive correlation between the number of doctors in a state and the number of deaths per state, deaths per year in the state. So apparently states with more doctors also have more deaths. That's a statistical fact, by the way. Can't argue with that. States with more doctors tend to have more deaths. What can cause that? Not cause that, but what can be a lurking variable to explain the connection there?
A large population.
Population.
Sorry, my dog's owner, my cat's, yeah, why I can't get the word out of my mouth. My bird's owner thought she was being funny, but she wasn't. What was your joke, by the way?
Medical malpractice is a real thing.
Medical malpractice is a real thing.
Yeah,
That's right.
why more doctors is deaths.
Probably not. It's probably because of the population's higher. So, so states with more doctors probably have a higher population. Is that what you guys said? Because I was being rudely interrupted.
Yeah,
Yeah,
there
okay.
was a higher population, more deaths.
Right, that makes sense, right? So population will be a lurking variable. B, many parents have noticed an association between their child's consumption of sugar and hyperactivity. Consumption of sugar, how much sugar you have, and hyperactivity. What could be a lurking variable behind that one?
Candy store.
Say again, hold on. So one more time, say that.
There's a close candy store. Okay.
Well, no, we're not giving a reason why you would have more sugar. We're trying to understand why there seems to be this correlation between how much sugar kids have and how hyper they are. I'm trying to understand. Yeah.
I mean, it does make sense. Because
Well, but does one cause the other, or is there a lurking variable behind the scenes? That's the question.
The sugar causes the hyperactivity.
Yeah.
If the sugar causes the hyperactivity, then that will kind of defeat the purpose of the exercise, which is saying that there's a lurking variable behind the scenes. Because if one legitimately causes the other, then there's no lurking variable. This causes that. Move on.
Oh, I see what like, for example, like there might be a high consumption of sugar, for example, like Halloween, but it doesn't correlate how high their hyperactivity, because they could be hyperactive naturally without even sugar. So there's also those.
Well, if they're hyperactive without eating sugar, then, let's put it this way. If they were completely independent, if the amount of sugar you had no bearing on hyperactivity, then you should not have a big correlation. It should be a correlation of 0, because there should be no connection between them. The fact that there is a correlation means that in general, kids who have more sugar tend to be more hyperactive. But the exercise is claiming it's not a cause and effect relationship. There's a lurking variable, something behind the scenes going on. And I don't know. I always was thought it was just how much sugar you have. Right? I was growing up. It was always, oh, he must have had a lot of sugar today because he's off the walls crazy.
Yeah. But
this is claiming that it's not a cause and effect. It's more that there's just an association. And I don't know what that would be. I don't know. There's not really a statistics question. It's just like a common sense question. But I'm curious. So I'm going to check something very quick. I have here some old professors' notes on these files. I don't like using them because I
Wouldn't it
like,
be
yeah.
like the amount of sugar that causes?
But that's the thing. I mean, when you do a correlation, it has to be quantitative. If it's quantitative, what that means is that you have to have a scale on the x-axis and a scale on the y-axis. Therefore, the scale on the x-axis would be the amount of sugar, and the scale on the y-axis would be how hyperactive. And the claim is that the further you go to the right, the more sugar you have, the more hyperactive you are. Does that make sense what I'm saying?
Yeah.
So I'm gonna look here to figure out what their answer was, if I can find it. This is chapter 15, correct?
Yeah.
Scatter plots and correlation. Scatter plots. I can't find any with notes anywhere. Oh, here we go. Completed class notes, scatter plots. Okay, let's see what they said. What they said was, and then we'll ask whether it makes sense or not. What they said was, party time? What does party time mean? Here, I'll show you. This makes absolutely no sense. This is theirs. Right? So we have amount of sugar on the x-axis. We have hyperactivity. These are all the different children. It says party time.
So that they're celebrating a party? Is
I
it
get,
like how much sugar they use? And then like how, cause like they could, like a kid could just get excited like an apparatus without eating anything, I guess. But like,
I guess so.
I don't
So if kids I guess the more they party, the more they eat, and the more hyperactive they are. But it's the party time that's really the cause of both. I don't know. I don't. Maybe. How many? Maybe. I don't know. I don't know. Again, I would not ask a question like this that has such a vague answer. I have no idea. Anyway, C. The CSU has found that students who take more math in high school do better in college. Ooh. So CSU's Academic Senate, which represents faculty at all 23 campuses in the system, approved a resolution calling for entering freshmen to take 4 years of high school math rather than the current 3. So why is it that students who take more math in high school tend to do better in college? Well, rather than have you guys figure that out on your own, unfortunately, I didn't close this down. You can see the answer here, is that people who take more math and have higher college GPA tend in general to either be more motivated, more serious, just might have better abilities, which are not inborn, but cultivated through years of study. And as such, will do better, not because the math makes them do better, but the kind of people who take more math are the kind of people who will just do better in college in general. So it's not that taking more math causes you to have a higher GPA, but again, it's the type of people who do more math are the types of people who would have a higher GPA. Who are they? Ones with a greater motivation and ability. Does that make sense? I didn't like the middle one. The first one was the simplest explanation, was obvious. This one also fairly obvious, but the second one I just don't like at all. So I'm gonna.
That was a really weird one.
Yeah, I'm gonna write a strongly worded email that I'm not gonna send to anyone because nobody would care about that. Okay, so that's chapter 15. We have just finished chapter 15. So let's now jump into chapter 16 on the other half of the coin of scatter plots, which is regression. Regression might sound very complicated and whatnot, but it's not. Regression is actually fairly straightforward. when you have a scatter plot and you believe that the scatter plot represents a linear relationship, the next thing we want to do is we want to create a line that goes through our data that best fits the data. It's clear that if I look at this scatter plot right here, we would all agree that this line is not the best fit of the scatter plot, right? I mean, the scatter plot clearly has a positive linear association, bottom left to top right. My line that I just drew is not the best fit line. What makes this black one the best fit line? That's a whole nother story. But the idea is that there is a unique, specific line that fits the data better than any other line, and that is called the best fit line or the regression line. Okay, so the regression line is the line that fits the data better than any other line, assuming that you have a linear relationship. Now, what's the point of making that line? The point of making that line is so that you can predict. Okay, I don't have any data for 42 centimeters here, right? I have here at 40 point something. I have here at 43 point something. I have no data anywhere for anyone whose forearm is 42 centimeters long, correct?
Correct.
But if I want to predict what the height in centimeters of a person would be with 42 centimeter forearms, my best prediction would be whatever the line gives me for that number. Because the line is the best fit, which means if you want to predict Y values, the line is the better predictor than anything else. So I would say that 42 forearms would be somewhere around 163 centimeters in height. Does that make sense?
Yeah.
Okay, the regression line is a predictive construction. So how well can you predict the size of a person's hands if you know their height? Spread the hand you don't write with as wide as possible and measure the distance from the tip of your thumb to the tip of your pinky. And write that distance in centimeters to the nearest tenth. So let's assume we did this. We're not actually going to do that because we're not in class together. But let's assume that you did that. And then you have your, we'll call that your hand span, and we'll call your height, right? And you, of course, know both of those. If we were to do this for everyone in the class, we might be able to construct a scatter plot. Now, do you think as people's hand spans go up, that their heights go up? Does that seem like a reasonable expectation?
Yeah.
Sure. So I would expect to have a scatter plot with a positive correlation. Here is not our class's scatter plots, but it is a class's scatter plot. Although interestingly enough, they did height on the x-axis and hand span on the y-axis, which is very strange because the question was, how well can you predict the size of a person's hand if you know their height? Oh, wait, no, that's what we want to do. Yes, I'm sorry, my bad. How well can you predict hand span if you know their heights? In other words, if I'm given this, how well can I predict this? Okay, so yes, the scatter plot works fine. Now, when you look at this data, does that look like it has a positive or a negative correlation?
Positive.
Positive. What do you say, strong, moderate, or weak?
Moderate.
Moderate at best, right? Moderate at best, it seems to me. Now they took this data and they plugged into a calculator because we don't do this by hand. And the calculator spat out the best fit line. And that's the line of negative 5.6 plus 0.4 times height. Does everyone agree that hand span is my y, height is my x, So this is the form of a line, is it not? Y equals mx plus
B,
b. What's the slope for this best fit line?
0.4
0.4. 0.4 what, by the way?
over,
Oh, wait, 0.4, what are the units of the slope?
centimeters.
It's not centimeters, but good guess. What are the
Oh,
units?
height, it's feet.
Still wrong, but thank you for playing. You were so excited that I almost felt bad shooting you
Isn't it
down.
inches? Darn.
Not
okay.
inches either.
Okay, never mind, I don't know.
Well, you're 0 for 3. I mean, you can't get 4 wrong in a row, so you might as well go one more time.
So centimeters?
Oh, I guess you can go 4 wrong in a row. Okay, so I take it back. Okay, so it's not.
That's why I give up.
It's okay. I'd rather have someone go 0 for 4 than someone sitting silently and do nothing. So thank you for trying, because that's what matters. Okay, Yoda was wrong. It's trying that matters, not doing. Okay, Yoda was an idiot. But anyways, that's besides the point. So what are the units of the slope? 0.4 what? So what's the definition of slope? How do we find the slope of a
Rise
line?
over run,
Rise over run. And what is the rise measured in?
centimeters,
And what is the run measured in?
inches,
So what should the slope be measured in?
Inches over
centimeters to
centimeters.
inches.
Rise over run. 0.4 centimeters per inch.
You don't use delta X over delta Y.
Well, first of all, it's delta Y over delta X.
Oh, right.
And second, no, I don't have to because they already gave me the slope. I don't have to calculate it. I know what it is. They told me it's 0.4. Okay, they just didn't give me the units. Because slope is rise over run, I use the units of rise divided by the units of run. 0.4 centimeters per inch. And that makes sense if you think about it. Because what it's saying is, for every inch that I go this way, my hand span goes up by how many centimeters? For every inch that I move to the right, my hand span would increase by how many centimeters? For every inch that I move to the right, my hand span goes up by how many centimeters?
0.4?
0.4. 0.4 centimeters per inch. For every inch this way, go up 0.4 centimeters. If I go up 2 inches, it should go up 0.8 centimeters and so on. Does that make sense? 0.4 centimeters per inch? Does the units
Yeah.
make sense?
Yeah.
Okay, now what is this guy here? Negative 5.6. What does that mean? Not whether, not does it make sense, but what does it mean?
It's the, I'm trying to remember my algebra. It was my favorite class. I'm not gonna lie.
So what happened?
I had to take elementary math for college.
That's true back for anyone.
I would say, doesn't it like the amount of spacing to the right?
So no, negative 5.6 is B. And what is B in a line? Y equals mx plus B. What's B?
The y-intercept?
The y-intercept. The y-intercept is the point 0, comma, negative 5.6. And that tells me that if I were to continue this best fit line all the way down to where x is equal to 0, which is way down there off the graph, that the hand span of a person whose height is 0 inches would be negative 5.6 centimeters. Is that a reasonable physical value. Doesn't make sense for someone whose height is 0 inches to have a handspan of negative 5.6 centimeters.
That doesn't make sense.
That does not make sense. So why can we trust a model like this one with a clearly nonsensical prediction? And before you say, you're right, let's throw out that model. No, the model's good. The model's fine. But the prediction of the model makes no sense. And we have to understand why. Anyone want to take a guess as to this one? Why does this model give us such a nonsensical prediction and yet is a valid model for us to use?
Because we put a
Me.
nonsensical height.
Because we put a nonsensical height.
Sorry for whoever I cut off.
No
It wasn't me, so it's okay. So, I'm just joshing. That was funny. Nobody laughed.
worries.
Yeah, that might have been worse not to even hear that, but that's okay. Anyways, so the data that we have in front of us extends from 62 inches of height to 74 inches of height. We don't have any data past 62 to the left or past 74 to the right. Because of that, we don't know that the trend that exists between those values continues beyond those values. That's called extrapolation. Extrapolation is when we try to infer something about values outside of a data range. We're extrapolating. We can interpolate all we want. We can predict things about inside. If I had someone who was at 63 inches, 63 inches is within my data range. I can predict all day long what someone with a height of 63 inches would have as their handspan. Whatever my line gives me, that's my answer. But there's no indication that that line continues the same way past 62. In fact, it can't, because it predicts that someone with a height of 0 would have a negative 5. It just doesn't even make sense. So somewhere along the line, the trend dies, and I don't know exactly where. So don't use it outside of your data range unless you feel that you are allowed to, on a case-by-case basis. Does that make sense so far?
Yeah.
Okay. Now, in general, what handspan does the equation predict for a height of 68 inches? If somebody had a height of 68 inches, how would I use that equation to predict their handspan?
You put it in the area of height, so you would multiply by 0.4, and then you add it to negative 0.56, and that gives you your prediction.
That is entirely correct. And what do you get?
I did not calculate it. I said it out loud. Give me a second. 21.6.
21.6. Do we agree? Everyone?
Yeah.
Does that make sense? So if you want to predict, all you got to do is plug it into your regression line, and out will pop the value as long as it's in the region that you're allowed to use. So 68 produces 21.6. 21.6 is about there. And if I put in 70, for example, what would it predict? I get 22.4. And why did I do those 2 points? Because now oops, it's a little off. It's not perfect, but something like that would be my best fit line.
I'm sorry. So you're using the y equals mx plus b equation or no?
Yep, this is the y equals mx plus b equation right here.
Except you're
Y.
putting in the 68 inches.
I'm sorry.
So like for the what hand span does the equation predict for a height of 68 inches? So you're putting in the 68.
Yeah, put 68 in there and I'll pop to 21.6.
Oh, okay, got it.
Now, it certainly looks to me like 1, 2, 3, 4, 5 points above and 18 points below. I would not imagine that that's the correct best fit line. Unless my graph is off.
I have a question on the graph. Why did you put the dot above 66 inches?
That's why it was 68
Okay.
inches. It was 68 inches, right?
Yeah.
Okay, that's why I'm like, this doesn't look like it should be the right answer. So 68 should be 21.6. Okay. That's much better. Okay. So let's draw that line instead. Okay. Okay, that's much better, isn't it? Even that's not the greatest.
And why did you make the another point on top of where the 70 is?
Well, I needed 2 points to make a line. Right? In order to make a line, I need 2 points. So I did 68 and then I picked one for 70. And I plotted both of those points and then I made a line through them. Yes, no?
So you just chose at random?
Yeah,
Yes.
I just picked one.
Okay.
Just needed 2 points. Does that make sense?
Yeah.
Yep.
All right. So let's first clear all that. Now let's keep going. Now, it says compute the hand span, the line. Okay, well, we can't do your height. Maybe we can't. Well, no. Actually, we can. Does anyone? No, we can't do that. Never mind. We can't. Unless someone has a ruler in front of them, we can't do this. So let's.
Well, I did. I actually did have a ruler and I measured my hand.
You did really? Awesome.
Yeah.
Okay. So what is your height and hand span?
5'7", which
Wait,
would
5'7",
be,
it's 67 inches. Right?
oh, I didn't even know. Yeah. And my hand span was 22 centimeters.
How much?
22.
22.0?
Yeah.
Okay,
Pretty much.
22.0, pretty much. Well, we're measuring to the nearest tenth, so let's just for the sake of argument say that it's that. Okay, so this is our data point right here. Okay, now, according to the best fit line, what would be your predicted hand span for a height of 67 inches?
About 22.
Not about. What does the equation give us? Let's do the math. What does the equation give us for a 67-inch height person? What is the predicted hand span for a 67-inch person?
21.2.
21.2. And I had someone in chat say 21.6, but no, 21.6 is for a 68-inch person. For a 67-inch person, it should be 21.2. Oops, okay, I'll forgive you. That's one time. So what we have is, this is the actual, this is your actual and 21.2 centimeters. That is your predicted. This is what the line predicts that someone of your height should be. And this is what you actually are. So what we can compute is actual minus predicted y, which is the actual y value, minus y hat. We call that y hat. It's a little caret symbol, but it's called a y hat is the predicted value. So the actual is 22. The predicted is 21.2. So therefore, what is the actual minus predicted?
0.8.
0.8 and centimeters. And we call this the residual. The residual, or the error in prediction, is how far off the actual value is from the predicted value. Graphically, I'm going to draw my best fit line again. So 60, I'm going to connect. Okay, well, I have to. Okay. So I'm going to draw my best fit line again here. Whoops. So there we go. So we know that 67 is 21 point, actually 66. 66, 64, 60, I think 6, okay. 66 is 20.8. So 20.8 is, I guess, around there. And if I do 74, that's exactly 24. That's a nice number. I was trying to get two nice numbers. So 74 is a nice number. And $64 should be a nice number. Yeah, 64 is 20. Okay. Lovely. So I don't need this one. I have two corners. So this is the best fit line. Okay. And now you had, your height was what, 67, we said it, correct?
Yeah.
And your actual value was how much?
20.
22, right? So this is your actual value right there. So this distance, vertical distance right here, that vertical distance from the actual points to the line above or beneath it, this guy here is called your residual. Every point has their own residual. They all have their residuals. So their residuals graphically, the vertical length between the actual points and the predicted points. All right, all with me so far?
Yeah.
Okay. So if the residual is a positive number, that means your actual is bigger than your predicted. And your hand span is larger than average for a person with your height. If your residual is negative, your hand span is smaller than average for a person with your height. And if your residual is 0, then your hand span is average for a person with your height. Make sense?
Yeah.
Okay. So now, how do we go about actually finding this best fit line? This is the question. So here's a situation where we have 4 data points. Now, a student suggests that the best fit line is the one that goes through the most points. Oh, yours goes through more points. It must be better. In that case, would that line be the best fit line of these 4 data points? It goes through 2 of them. It can't get any better than that. How is that as my best fit line? Would you agree with that? Is my best fit line for these 4 data points?
No.
No. How about that? Is that the best fit line? Or that? Best fit line?
No.
How about that? Would any of these be the best fit line for those 4 points?
No.
No, I don't think so. I mean, I would think something else like this would be like the best fit line, right?
Yeah.
Okay, but none of those. I mean, what you just said was like the best fit line, something like that, doesn't go through any of the points. So the number of points that it goes through does not seem like it's a determining factor. So one person says, fine. As long as it has half the points on one side and half the points on the other side, then now that makes it the best fit line. I'm like, oh yeah, that's a great idea. Let's do that. That has 2 on each side. Is that the best fit line?
Nope.
How about this? Best fit line?
No.
But it has 2 on each side. So that can't be it, right? We just did a couple of examples where you're like, listen, you think it's this, but that doesn't make sense. So one person says, oh, I have an idea. Let's do a little more math. I have an idea. Let's draw a hypothetical best fit line. Okay, I say this is the best fit line. So what this student suggests is as follows. Calculate all of your residuals. There's going to be 4 residuals here, right? That one, and that one. 4 residuals. What one person says is calculate all 4 residuals. Take the absolute value of them because we don't want negatives. We don't care if it's below or beneath as long as it's off what it should be. So I don't care about positives or negatives. So make them all positive and add them all together. That's going to give you a number, correct? Right? If you compute the 4 residuals and add them together, that gives you a number, right?
Right.
Now imagine we did that for a different line. Imagine we did that for this line. So I can go ahead for that one and compute my 4 residuals. 1, 2, 3, and 4. I can do the same thing for that one, right? And add them together and get a number. The student suggests pick the line that gives you the smallest of those numbers. So if the blue one gives you the smaller total, that's a better line than the red one. What do you think about that idea? Think of every possible line in existence, calculate the residuals, absolute value them, add them together, and then out of all the lines in existence, pick the one that gives you the smallest total error. What do you think of that idea in theory? Anyone?
Wouldn't that be considered like biased against like the errors that were calculated?
What do you mean the errors that were calculated?
Like,
yeah.
because what you're saying to pick the one with the smallest residual, right?
The smallest total residuals. You're going to add them all up together and pick the one whose sum is the smallest. So for like the blue line, you'd add up all 4 residuals. 1, 2, 3, 4, add them together, add their absolute values together, and that gives you a number like 17, whatever the number is. And then do the same thing for the red one. Add this one and this one and this one and this one and get that number. And whichever those two numbers is smaller, that's the better line. Does that seem in theory like it'll be a better determination of the best fit line than the other methods above it?
Yeah.
It's not bad, actually. It's not a bad idea. It's not 100% correct, but in theory, it's a great idea. There's two problems with it. One problem is how do you go about looking at every conceivable line in existence to determine which one has the smallest sum? All right, we're claiming, look at every possible line that you might ever want to draw and pick the one that gives you the smallest sum of the errors. Well, there's infinitely many lines. How do you look at them all? So the answer to that is, don't worry about it. The methods of calculus, which unfortunately we can't learn, can get around that issue. The methods of calculus allow us to look at all of them at once and pick the one that's best. The problem with that is that calculus does not work very well with absolute values. So what we're actually going to do is something very similar. We're going to instead, although that's not for a couple pages yet, instead of absolute valuing them to make them positive, we're going to end up squaring them to make them positive. But that is kind of what we're going to do. So let's see it in action. Do you guys remember the mean absolute deviation that we did a couple chapters ago? Does that ring a bell at all? Anyone? Hello? Anyone? Anyone?
I don't
I
remember.
remember MAD.
You remember the MAD, right?
Mhm.
Well, if you don't recall it, here's the formula for it. So we're going to do here, this is 3, this is 7. So we're going to pick 5. And here, this is 3, this is 13. So halfway through 3, so 5 and 13 is 9. So I'm going to draw this as my best fit line. And what we're going to do is we're going to calculate the sum of the residuals. Let's see what we get. So for x is 2, the actual y is 3. But what is the predicted y for that x value?
5.
5. Which gives us what residual?
-2.
-2. Next x value, 2, 7. What is the predicted for that one? What is the predicted x value? Sorry, y value for x equals 2? Well, it's still 5. It's the same x value, so it's the same prediction. Right? Anyone? Have I lost you all?
Yeah, makes sense.
So therefore, and what's the residual for that one?
2.
+2. For this one, if we look at this guy here, 8, 5, what's the predicted value for 8?
9.
9. So these are both 9. What's the residual for that one?
-8.
-4.
4.
Oh, 4. My bad.
And how about for this one?
Just regular 4.
Just regular 4. So if I add up their absolute values, those differences, what do I get?
0.
Absolute values, not the actual numbers. with the absolute values of the numbers. Make them all positive and then add them. What do I get?
12.
12. Right, Sabina, 12. Okay. Make sense? So for this line, the sum of the residual error, the sum of the absolute values gives us 12. Now, if I were to go ahead and try a different line like this one, for example, let's go ahead and go through these. What is for the first X value, which is 2, 3, what is the predicted value for that X value? What is this number here?
7.
7. And that'll be for both of these. And if I do 8 and 5, what's the predicted value for that one? What's the Y
5.
value? 5. So what's the residual here?
-4.
And this one here?
0.
And this one here?
0.
And this one here?
8.
And when you take their absolute values and add them, what do you get?
12.
We get the same number, 12. But I think it's clear, I hope it's clear, that this one here is a better fit of the data than the blue one, but yet we got the same value for both. We got the same value for both. So the problem there is that with absolute values, you're always going to get 0, or not 0. You're always going to get the same value for every line, which is why absolute values are not the way to go. What we do instead is use the sum of the squares rather than the sum of the absolute values. And as we're going to see next time, because we're kind of out of time today, and we're going to finish this chapter next time and go further, we'll see that that's a much better way of getting it. But at the end of the day, your calculator is going to do all the work for you. That's what it's going to come down to. Anyway, we'll stop here a couple minutes early because I can't really get anything done in the next 3 minutes. So I will see you all on Thursday.